Hello, I'm Min-Jung Lee, the second semester of the master's course in artificial intelligence at Korean University. I'm start the final project presentation. Project title is How to Accelerate Diffusion Model Training. First, I'm gonna talk to introduce the problem. As the complexity of the data distributions, I aim to generate continuous to increase training diffusion models to convergence has become extremely computationally demanding. For instance, training images with the widely known stable diffusion model requires a staggering 24,100 GPU hours. Moreover, video training is even more resource-intensive. A diffusion-based video model demands 48,800 GPU hours. Given these massive computational demands, accelerating the training process for diffusion models has become a crucial challenge in the field of machine learning and artificial intelligence. Regarding the goal of this project, to address this challenge, this project focuses on developing an algorithm that can effectively accelerate the training of diffusion models more effectively than existing methods by being adaptive to the training process. Now, let me talk you through the method I proposed for improving the efficiency of diffusion models. My approach focuses on pruning, which is a widely used technique to reduce computational cost and enhance model efficiency. Structure pruning. This method focuses on removing channels in the neural network, which effectively reduce an actual number of parameters and computation required by model. On the right, an illustration that visually demonstrates the effect of structural pruning. Before pruning, we see the fully connected structure of the model. After pruning, the several nodes and their connections have been removed, reducing the model size and complexity. In contrast, unstructured pruning merely sets certain weights to 0 without actually reducing the model size or computation. Therefore, rather than using unstructured pruning, I propose to use structured pruning as it helps reduce both the computational cost and the training time with improving overall model efficiency. Importance criterion is tailor-based scoring. To decide which parts of the model to prune, I employ a tailor-based importance criterion. This involves calculating an importance score for each output channel of the layer based on its contribution to the loss function. Specifically, as shown in the formula, calculate the first-order Taylor expansion of the loss with respect to the parameters, assuming over the contributions across layers and time steps. The pruning process then removes channels that are deemed less important, effectively introducing sparsity in the output channels of the diffusion model. The primary task for this experiment is image generation. I aimed to generate high-quality images using a prone diffusion model while maintaining or improving performance compared to the baseline. For this experiment, I used tiny ImageNet dataset as a miniature version of the ImageNet dataset. Datasets are suitable for experiments and learning due to their high memory and computational efficiency, as our images are fixed at 64 by 64 pixel sizes and small image sizes. The class consists of 200. The training dataset consists of 500 images per class, a total of 100,000 images, and the validation dataset consists of 50 images per class, a total of 10,000 images. As a baseline, I compared my pruned model against the widely recognized Stable Diffusion model. In terms of pruning, I specifically target the convolution to the layers within the U-Net architecture used for the denoising process in diffusion model. The U-Net architecture is central to many diffusion models, as shown in the diagram below, where it progressively refines noisy input to generate clean images. To evaluate the effectiveness of our method, I use two main metrics. First, I calculate the FID score to assess the fidelity and diversity of the generated images. A lower FID score indicates higher image quality and diversity. Second, I measure the multiply accumulate operations, max, and the number of the parameters to quantify the degree of weight reduction in the model. These metrics help demonstrate the computational efficiency of my pruning approach. Next, I'll present the result of this experiment and demonstrate how pruning method compared to the baseline in detail. Time step was set to 1000 steps and the sparsity was set to 0.3. To evaluate pruning and performance, I used the DDIM sampler. Additionally, to fine-tune the model after pruning, I retrained it for 50 epochs. Performance result is here. The FID score increased from 3.6 to 9.16. This shows that pruning had an impact on the generative quality of the model. The computational cost represented by max was reduced from 598 to 311, achieving a reduction of approximately 51%. This indicates significant model compression and efficiency gains, and the number of model parameters was reduced from 400 to about 200, a decrease of about 55%. This demonstrates a substantial reduction in the model size. The pruning process was successfully reduced max and parameters by around half, significantly improving model efficiency. while the FID score increased slightly. This can be seen as a trade-off for the achieved compression and reduced computational cost. This is all of my presentation that I prepared. If you have any question, please contact me by the email. Thank you.